looks kind of scary with this whole polynomial, but again, if this is our polynomial, where this is our leading term, right, and this is our constant, those are kind of the big important things here. So if you have integer coefficients, every rational zero will have the form, we say P over Q, where P is a factor of the constant term, and Q is a factor of your leading coefficient. So if you just take all the factors of the constant term and divide it by all the factors of the leading coefficient, you'll get a list of possible rational zeros. These can still take a while to find the ones that actually work, because they don't all work, but instead of guessing from every possible real number, it gives you this list of numbers to check. All right, so I call these PRZs, possible rational zeros. So I say PRZ. When I do my homework, when I do a test, I say PRZ is equal, so I don't have to write them all out. So again, kind of just restating it. We're going to take factors of the constant over factors of the leading coefficient. Really super great when the leading coefficient is 1, because that means we're just dividing by 1. So we don't have to check any fractions. This is where using the remainder theorem yesterday is helpful, because if we didn't have the remainder theorem, we'd have to synthetically divide all of these possible rational zeros to see which ones work. But we can just plug them in and see what works. So let's do one and see if your memory holds up here for us. So it says, use PRZs to write a list of potential rational zeros. I say possible rational zeros. Then determine which ones, if any, are zeros. So, step 1. We're going to write it out a lot on this one. We're going to take factors of the constant. So we're going to take factors of negative 14 divided by factors of the leading term, which is the one with the highest exponent, usually first, factors of 3. And then you have to work out all the possibilities. So, factors of 14, what you got? 1, 2, 7, and 14. And notice it's negative 14, and think about, you can put the negatives whichever way you want, right? You could say negative 1 times positive 14, or you could say positive 1 times negative 14. So we count for that by just doing plus or minus, right? Plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. It's always fun when like 36 is one of the factors. That's a lot of terms there. Factors of 3, 3 is a prime number, right? So it's just plus or minus 1, plus or minus 3. Remember doing this last year? And so then you just have to work out all the possibilities. And so I don't know, however you see it. For me, I just always go through and like put all the numerators over each denominator and work it all out. So everything over 1, so my list of PRZs is going to be 1 over 1, which is just 1, 2 over 1, which is just 2, 7, plus or minus 7, plus or minus 14. But then I also have to put them over 3, and you want to reduce, and if you ever reduce it, and it's already something you have, like you don't have to repeat it. None of these are going to repeat. But then we'd also get 1/3. Oh, I didn't write enough down. Right, scoot over now. Plus or minus 2/3, plus or minus 7/3, plus or minus 14/3. With me on that? And 16. We have 16 possible rational zeros. That's a lot. But it's less than if I just asked you to randomly pick what numbers work in that problem. So this kind of just gives you some, clarification on what to pick. This says, now determine which ones, if any, are zeros. This is where it just takes some time. You have to plug them in. You have to see if you get 0, then it will be a 0 or a factor. I always have this hope that 1's going to work. Right? 1 or negative 1, yes, ma'am.
Which ones are the P's again? Because I think I did it all fixed.
Factors of the constant on top, factors of the leading coefficient, right?
So P over Q.
right? Like, so you take factors of the constant, P over Q, where P is the constant term and Q is the leading coefficient. So you got to have the end term over the first term. Did you do 3 over 14?
I don't know what I did. Like, with the piece here,
No, this is right. So this is, P is factors of the constant, which is 14. You did that right. This is right. So, but now you have to like simplify this fraction. So 1 over 1, so 2 over 1, 7 over 1, 14 over 1.
Okay, that's what I did.
Right? 1 over 3. Yeah.
Sorry.
Okay, so I think you mislabeled this.
Oh, okay.
Right? So this is P down here. And this is
Thank you. Sorry.
No, you're fine. That is the number one mistake that happens is on the test is people flip it around and they do the leading coefficient over the constant. So you just have to check. This is where if you don't have a calculator, I'm going to throw one at you. Test your sketching skills. Or you just have to plug them in. So me doing all the work. Wait, no, you put your hands up. See if someone around you needs one. Anyone else? Levi, you have a calculator? You have a calculator, you have to get it out. If you don't have one, you have to get one from me. Here. Those are the opposites. You have a calculator? So you have to just check. Sometimes you get a really good feeling like, I think it's 7/3, right? And you're going to plug it in. Sometimes you just check them all. Amazingly, when they're on the back of the book, you always guess the right one the first time. I always start with 1 and -1 in hopes that I can do it in my head. Or maybe I see that it's not going well on these. Right? So I'm going to use a calculator too, but for the first ones, just to kind of show you, I don't care what it equals, I just care if it equals 0. So if it doesn't equal 0, I just move on. So I just look to see if my my negatives and positives cancel out. Definitely not. So that does not work. Does not equal 0. If I plug -1 in, I would get -3 -7 -6 -14. I take a minute sometimes to do this on the first ones and show it because sometimes it helps me reduce my number of options. Look what happens when I plug a negative number in there. You notice when I plug in a -1, all of the terms turn negative? You see that? So am I going to check any more negative numbers? Because I can see when I plug a negative in, it's just getting more negative. So why would I pick any more negatives? So I just reduced my number of PRZs by half by taking a second to write out what's happening. Sometimes if you plug something in and you notice it's all positive, well, that's never going to go to 0. So I'm not going to check any more negatives. I just saved you some work there. Now we have to just go from here. You find one? I got -6. Did someone find one? What'd you find?
7/3.
7/3. Oh look, I totally said that.
That's fine. I figured they'd use like 2.
No, I really didn't even know the answer.
So I was like,
So if you haven't checked 7/3, check that really quick. One, you want to make sure that you can do the fractions on your calculator. Right, so on my calculators, if you're taking 7/3 to the 3rd power, I probably put parentheses around that. And then I want to show you how we don't have to keep checking, okay? We could just keep checking the other ones, but I want to show you other options. So, squared plus 6 times 7/3 minus 14 equals 0. Okay, so we could have 3 real zeros here. We could have 3 numbers here that work. But for me, I know eventually we're going to get to the point that we want to find all the zeros, even the ones that aren't rational, even the ones that aren't real. So for me, I despise this part of this problem. I despise just typing in my calculator and seeing which one equals 0. So as soon as I find one, I'm going to divide that out and look what's left and see if I can factor it, because I don't want to keep checking every single number. All right, so for me, once I find one, I'm going to say, okay, 7/3 works. I'm going to do synthetic division So look what polynomial is left after I divide that out. So, I know it's a fraction, but don't freak out about that. 3, negative 7, 6, negative 14. And it works out really nice. We already know it equals 0, which means we should get 0 down here. You have a question on where I'm getting this from? And when I take 3 times 7/3, the 3's are just going to cancel out, right? And I'm just going to get 7. And then negative 7 plus 7 is 0. And then 0 times 7/3 is 0. And then I get 6. And you can use your calculator here, but 6 times 7/3, you're going to cross out the 3 with the 6 and make that a 2. 7 times 2 is 14, which does give me a 0 here. So I found one that works. I divide it out, and then look what's left. This was x to the third, so I know that this is going to be 3x squared plus 0x plus 6. That's my new polynomial. Why is that really nice? Because we know how to solve quadratic equations. We don't have to just guess numbers and see what works. We could solve this. I guess I should have just said that equals 0. And here's what's really great if you can see it. We only want real numbers here right now. We don't want imaginary. So right away, I see that this isn't going to give me a real number, because if I subtract this, if I take the square root of a negative number, that's going to be complex, yes? I don't want complex numbers right now, so this is not a real number, which means the only answer that I want to give is 7/3. For me, I can do this way faster than I could check all those numbers. Now, if you've checked them all and you only have 1 or 2 left to check, go ahead and check them all. That works. But just know that eventually we're going to want the complex numbers too, and you'll have to do this anyway. So I feel like this is like good strategy going forward. But you don't have to do that today if you don't want to. Questions about that? Once you find one, you can divide it out, right? Like every time you find one that works, you can divide it out and see what's left. So if it's a third power polynomial, once you find one and you divide it out, you'll always be left with a quadratic, and we know how to solve quadratics, whether it's quadratic formula or factoring or complete the square.
Right, but I mean, like, I don't have to go through the rest of my PRGs after I find it.
We don't have to go through the rest of our PRZs because this, if there was another PRZ that worked, we could have solved this and got the answer there. Does that make sense? We'll do one in a second that maybe has more PRZs. Because we can solve that to get the rest of them that work. When you get all the answers that work, or when you get something that's not real, that's when you stop. Because we could solve this. Like, we know how to do this. We've done this last year. We could say here that x squared equals negative 2 and x equals plus or minus I radical 2. In section 2.5, that's where we're going to go. We're going to say find all the zeros, both real and complex. But in this section, they don't want you to give the imaginary ones, so that's why you can stop when you get to something that's not real. Okay? Yes?
You can use synthetic division to find the first root too, right? Instead of plugging it in.
Oh, yes, definitely. So if you wanted to do synthetic division as you go, and then that way you don't have to go back and do it, you could do that as you go. Totally. Did you guys do that last year? Did you do synthetic division on all of them instead of plugging them in? Oh, that's terrible. That's a whole lot of work. Like, what if you had to do synthetic division on all of those until you found one? That's a lot of work. You can. I mean, it saves you from having to do it again, but yeah. I don't do synthetic division until I find one that works. But yes, if you want to synthetic, please find it. You can. Okay, let's do another one. Step 1, find your PRZs. Factors of the constant. Factors of the leading coefficient. On a test, this would be like something I would give you on a test. On the homework, there may be one that has some really, really, like a lot of PRZs. It also may be odd, which means, you know, you get a little help picking that first one. or minus 9 halves. I can't believe you synthetically divided all those. All right. Oof. I was thinking about doing it, but I don't think I would. Oh, so close. Oh, that doesn't work. Anybody found one yet? Yes. 3/2. See, wouldn't this be great if we all worked together on all of our homework? Someone would be. To just go straight to the fractions, assuming that's what's going to work. I always hope that one works. Okay. So 2 times 3 halves is 3. 2 times 3 halves is 3. Negative 6 would be negative 9. We also did, in Algebra 2, you did that Descartes rule of signs. Remember that, where you would kind of look? They don't really emphasize that in this book, and we'll talk about it in section 5, like if you want to use that as a helpful thing of like how many real zeros, how many positive real zeros, how many negative real zeros. But they just don't really emphasize it that much in this book. So again, how do you know when to stop? You find one, divide it out, look what's left. So you're left with 2x squared plus 2x plus 6. And I'm just going to set that equal to 0 because I just want to find, are there any more rational zeros, is what the directions say here. Find the PRZs that work. And so since those are all divisible by 2, is it okay if I divide everything by 2 here? So I'm going to say that's x squared plus x plus 3. Yes? Is that factorable? Did I do something wrong?
Yeah.
Thanks. You just gotta tell me, kids. Is that factorable? And the only thing that multiplies to give me 3 is 3 and 1. If it's not factorable, can it be a rational root? It could be real, but it's going to be irrational. Like there's going to be a radical left. The directions here just said find which PRZs work, which means this is not factorable, which means it's not rational. Which means, yet again, I can stop because I'm only verifying the list of PRZs up there. So I don't care what happens from there if it's not rational. Which means, again, the only rational root on this is 3s.
So if it was rational and I could factor that, I'd keep going.
Yes. So let's just pretend, okay? Let's say we got this. If that's what was left, right? Then we can say, oh, that's x and 2 and 1 plus 2 minus 1. X equals 2, negative 2, x equals 1. Those would be in my list up there, and instead of having to check them, I could find them by factoring. You could still find them by just checking them all. If you want to check them all, check them all. But for me, this is a faster way to do it to determine if I can find more. Okay? But so yes, if it is factorable, then we would go there. Okay. All right, last thing is this idea of upper and lower bounds. This is really helpful if you're synthetically dividing on all of them the way that you did in Algebra 2. You can look for these upper and lower bounds, which kind of just eliminate some of your options in your PRZs. They're kind of wordy. This is the reason I printed your notes out right here. Says if you have a polynomial with real coefficients and a positive leading coefficient, and you were dividing by some x minus c using synthetic division. All right, so if you're dividing by a positive c value, And each row in your synthetic division, I wrote each number in the last row. That means like if you have a number here, whatever. Down here, this is the last row. So if each number is either positive or 0, then you can say the number you are dividing by is an upper bound. What does that mean? It means there'll be no zeros bigger than that number. So if you divide and all the numbers are positive, you know that there's no other zeros bigger than that. So if you had some PRZs left that are bigger, you could exclude those. So that's where using synthetic division, you could see that. Doing it the way where I just plug it in, that doesn't really help much because I'm not synthetically dividing all the time. What if you're dividing by a negative number? So if what you're dividing up here is negative, and what's left in your last row, alternate signs. So they alternate positive and negative. So it goes positive, negative, positive, negative, negative, positive, negative, positive. And notice that 0 really just doesn't count for anything. It could be either one. Then we say that that is a lower bound, which means there will be no zeros less than that number. All you really have to do is memorize the rule for this. And then there are questions that say, show this, is this a upper or lower bound? And you just synthetically divide and you just look to see. And then the goal is, if you're synthetically dividing, then this can help you eliminate some PRZs as you go. All right, so let's look at a couple examples here. I think that's it for me. And your homework says exactly this. Use synthetic division to prove that the number k is an upper or lower bound for the real zeros of the function. If it is a positive number that you're dividing by, the only option is it could be an upper bound. Because if you divide by a positive number, it's an upper bound. If you divide by a negative number, it could be a lower bound. So this is either going to be an upper bound or it's going to be nothing. All right, and you can tell that very easily by looking at the sign. And all we're going to do is do synthetic division. Fill in zeros as necessary. This one doesn't need any. I break this down. 2 times 5 is 10. 25. 20. 100. 99. Definitely it's not a 0 of the function, but the fact that all of these are positive tells me that 5 is an upper bound. I took this problem directly out of the textbook, and then I think it's kind of a silly problem, because if I thought about my PRZs for this, are there any PRZs bigger than 5 for this function? No, so why are they even having me check 5? Because there's no PRZs bigger than 5. So I thought it was kind of silly. But it definitely shows the point that these are all positive. Yes? If it was 1 negative, we would say it's nothing. It's not a bound. Because it would have to alternate signs to be negative. It would have to go positive, negative, positive, negative. You see what I'm saying? And, yes. And also, to be a lower bound, you have to be divided by a negative number. So the nice thing is, if I give you a question like this on the test, if it's positive, you know it has to be upper or nothing. Okay? So I think I just put a lower one on here too, right? Because that's negative, it's either going to be a lower bound or it's going to be nothing. And to show it's a lower bound, you just want to show that it alternates sign, positive, negative, or negative, positive. And this one is actually at least a relevant problem because there are going to be PRZs less than -1. -3 would be a PRZ. So you're just kind of looking for the pattern. Positive, negative, positive, negative. So because it alternates sign, we can say that we know -1 is a lower bound. There's a couple, maybe one question about a graph. We'll probably talk about it whatever day. If we have time tomorrow, we'll talk about it. And if not, we'll talk about it on Thursday But it's just kind of having you use this idea to help you know if there's another 0 outside your window. Okay? Oh look, how is this not on the graph? Oh look. How did I just not print all this? Look at this. Well, it's not on the graph. Okay, the bell's gonna ring, but don't leave yet. What if the directions said find all the real zeros? If it said find all the real zeros, that means when you divide out one of the zeros, you still have to check to see. You might have to do the quadratic formula, right? But I don't want imaginary zeros, and we'll talk about this on Thursday because for some reason I didn't get through any of this. Okay, but write this down. Or actually, yeah, right. I have assignment sheets for you. If you don't want to write this down. If we have time left tomorrow after we're in the gym for tapping, bring your stuff back here. I swear that I just was missing a whole page of text. That was supposed to be